As another deriving method, we can use the parse tree. Parse tree is an ordered, rooted tree that represents the syntactic structure of a string according to some formal grammar. Parse trees may be generated for sentences in natural languages as well as during processing of computer languages such as programming languages. In BNF, parse tree is used as a graphical hierarchical representation of derivation. This distinguishes between non-terminals and terminal nodes. The inner nodes are called as non-terminals and the leaf nodes are called as terminals. Each node in the tree is either a root node, a branch node, or a leaf node. Root is a start symbol. A node can also be referred to as parent node or a child node. A parent node is the one that has at least one other node linked by a branch under it. A child node is the one that has at least one node directly above it, to which it is linked by a branch of the tree. Let's try an example. Here, expression can define as a term or term plus expression, and term can define as letter A or B or C or D. Let's consider the example A plus B. First, we can consider the expression as a term plus expression. A can assign as the term. Next expression can be defined by using a term and the B can assign as the term. This is a simple parse tree which you can get the idea about how to create the parse tree for a given expression and do derivations. Now we are going to try another example which is somewhat complex than the earlier one. In this example, ID can define as an expression. An expression can define as a summation of expression and expression 1 or subtraction between expression and expression 1 or just only expression 1. Expression 1 can define as a multiplication of expression 1 and expression 2 or expression 2. Expression 2 can define as variable or an expression inside brackets. Variable can define as x or y or z, and ID can define as A or B or C. Let's draw the parse tree for the example. A defines as z minus x plus y into x using a grammar describe. Here, there is a name given to this example as assign. We use it as the root of the parse tree. ID defines expression. We draw them as three separate branches. As for example, A is given as the ID, so we can put A as the ID and end the branch. Then we are going to the expression branch. Here we can derive the expression as a subtraction between expression and expression 1. We draw that derivation as another three branches which start from the expression node. The expression can define as expression 1. We link that node to the expression node. Then expression 1 can define as expression 2, so we link that node to expression 1 node. Then expression 2 can define as a variable. As for the example, z is given as the variable and we can put z as the variable and end that branch. Now we are going to tackle the expression 1 branch. Here we can define expression 1 as a multiplication of expression 1 and expression 2. Draw those as three separate branches which start from expression 1 node. From these three branches, first we are going to evaluate expression 1 node. There, expression 1 can define as expression 2 and expression 2 can define as expression within brackets. So, we draw expression 2 as a child of expression 1 and expression within brackets as a child of expression 2. This can evaluate as the summation of expression and expression 1. From them, expression can define as expression 1 and expression 1 can define as expression 2 and expression 2 can define as variable, and as for the example, we can assign x as the variable in there. The next child of expression within brackets is expression 1. As earlier I said, we can define expression 1 as expression 2 and expression 2 as variable, and we can assign y as the variable at that point and end the branch. Now we are going to solve the expression 2 node, the child of expression 1 node. Same method, we have to follow expression 2 can define as a variable, and as for the example, x can assign as the variable here. Now you can see we have completed our derivation for the example using parse trees. I hope you are clear with parse trees. Let's continue with uses of parse trees next. Ambiguity is a very important point in a language. In computer science, a context-free grammar is said to be an ambiguous grammar if there exists a string that can be generated in more than one way. We can track this using parse trees or using derivations. If there are two or more parse trees or derivations, that grammar is considered as ambiguous. Now, let's talk about a simple example. The shown BNF grammar is an ambiguous grammar. We can prove it using derivations and also by parse trees. In first way, we first consider about expression minus expression. Terminal A is assigned to first expression non-terminal value, and we expand the second expression non-terminal as expression into expression. In the next step of the derivation, we assign terminal values to expression. According to this way, multiplication is performed first. The second way, we expand the first expression as expression minus expression. In next step, we assign terminals from left to right. In here, we first get the difference of A and B and use that answer to perform multiplication with C. According to the order of the performance of the operations, we can have two derivations. Now, let's consider how to prove an ambiguous grammar using parse trees. As figured in the slide, there are main two parse trees for this grammar. In first parse tree, multiplication is occurred first, because we need that answer to perform the subtraction. But it's not the way in second parse tree. In second parse tree, subtraction is performed first and you use the answer of it to do the multiplication. Using the same language, we can have some unambiguous grammar. If we use brackets, we can see we will set only a parse tree, and also we can have one left mode derivation. In first one, we use brackets to perform the multiplication first. In second one, we want to do the subtraction first, so we use brackets to do it. We know unambiguity is a main characteristic of a good language, so we need ways to solve this ambiguity problem. In order to resolve this ambiguity, we can use some methods. One solution is using disambiguating rules such as precedence and associativity. As an example, multiplication has higher priority than addition. So, according to that precedence order, we can make the grammar rule unambiguous. Second solution is rewriting grammar to be unambiguous. Most of the time, there may be a dangling else problem as figured in slide. So, to avoid the ambiguity, we can use begin and end to separate the sections in the code. Last solution is the defining matched and unmatched statements. As figured in the example, we can directly define the matched and unmatched statements so that we can resolve the ambiguity. Extended Baker-Noah form. In computer science, EBNF or Extended Baker-Noah form is a code that expresses the grammar of computer language. The earliest EBNF was originally developed by Nicholas Wirth. However, many variants of EBNF are in use. It consists of terminal symbol and non-terminal production rules, which are the restrictions governing how terminal symbols can be combined into a legal sequence. These production rules define the non-terminal digit, which is on the left side of the assignment. Examples of terminal symbols include alphanumeric characters, punctuation marks, and white space characters. The International Organization for Standardization has adopted an EBNF standard. The representation of a grammar is made of a set of syntax diagrams. Each diagram defines a non-terminal. Each diagram has an entry point and an end point. It describes possible paths between these 2 points by going through other non-terminals and terminals. This slide represents the table of symbols that are used in extended Baker-Snor form. In here, it shows how to express an EBNF grammar when having a BNF grammar. By referring to these 2 examples, everyone can get a clear idea about writing EBNF grammar from BNF grammar. Syntax diagrams are a way to represent a context-free grammar, and this helps to increase the user understanding about the grammar defined. This slide shows the major principles used when drawing a syntax diagram. Let's try out an example given in the slide and see how the principles are used in drawing syntax diagram. In this example, expression is non-terminal and directly we can write term or term can repeat many times because of this have iteration loop has used. As this, we can draw the syntax diagrams for term and constant. To draw the syntax diagram for factor non-terminal, we can write it by through constant or variable or an expression with brackets. Because of that, we have to use all those non-terminals and link them to the main path. When drawing the syntax diagrams for variable and digit, also can use same method. But the difference of digit is we have to put 10 non-terminals to represent digits from 0 to 9. With the syntax diagram, you have covered all the related topics to Baker-Snor form. We hope this video helps you to clarify your problems, to enhance your knowledge and to get a clear idea on Baker-Snor form. Thank you.